Section 250.30 of the National Electrical Code requires that grounding conductors be of copper, aluminum, steel, or copper-clad steel. Section 250.104 ATWO allows the use of aluminum or copper grounding conductors, but specifically prohibits dissimilar metals in direct contact underground. Exception number 2 to 250.104 ATWO permits the use of connectors, fittings, and accessories that are listed for grounding and are suitable for the materials involved. The contractor's statement that the aluminum lugs are dual-rated for aluminum and copper connections does not necessarily mean that they are suitable for grounding grids. Direct contact between dissimilar metals in underground grounding grids can lead to galvanic corrosion, which can weaken the connection and increase resistance. The electrical conductivity of copper is higher than that of aluminum, so using copper lugs would ensure a better electrical connection. It's recommended to insist on using copper lugs for all grounding connections. This will ensure compliance with the NEC and minimize the risk of galvanic corrosion. If the contractor insists on using aluminum lugs, request that they provide specific documentation from the manufacturer stating that the lugs are suitable for use in grounding grids with both copper and aluminum conductors. To mitigate the risk of galvanic corrosion, consider these additional measures. Firstly, apply a corrosion-resistant coating to the connection point. Secondly, use a watertight sealant around the connection. Thirdly, inspect the connection regularly for signs of corrosion. While it is true that certain dual-rated lugs can be used for both aluminum and copper connections, it is not prudent to use them in direct contact underground and grounding grids. Insist on using copper lugs for all grounding connections to ensure compliance with the NEC and minimize the risk of galvanic corrosion. Galvanic corrosion is an electrochemical process where one metal corrodes preferentially to another when they are in electrical contact in the presence of an electrolyte. This process is relevant in the context of grounding grids because the earth itself can act as an electrolyte, facilitating the flow of ions between dissimilar metals. When aluminum and copper are in direct contact underground, the aluminum acts as the anode and corrodes, while the copper acts as the cathode. This corrosion can weaken the connection over time, leading to increased resistance and potentially compromising the integrity of the grounding system. The rate of galvanic corrosion depends on several factors, including the type of metals involved, the electrolyte composition, temperature, and the area ratio between the anode and cathode. A larger cathode area relative to the anode area accelerates the corrosion of the anode. In grounding grids, the large surface area of copper conductors compared to the smaller aluminum lugs can exacerbate this effect. The National Electrical Code addresses the issue of dissimilar metals in grounding systems to minimize the risk of galvanic corrosion. Specifically, Section 250.104 ATWO prohibits the direct contact of dissimilar metals underground to prevent corrosion. However, exception number 2 to this section allows the use of connectors, fittings, and accessories that are listed for grounding and are suitable for the materials involved. This exception is intended to provide flexibility in using dual-rated connectors that are designed to prevent galvanic corrosion. Dual-rated connectors typically use a barrier or coating to prevent direct contact between the dissimilar metals. These connectors are tested and listed by organizations such as Underwriters Laboratories to ensure that they meet specific performance requirements, including resistance to corrosion. To ensure compliance with the NEC and minimize the risk of galvanic corrosion, it is essential to select connectors that are specifically listed for grounding applications and are suitable for use with both copper and aluminum conductors. The manufacturer's documentation should clearly state that the connector is designed to prevent galvanic corrosion and is suitable for direct burial. In addition to selecting appropriate connectors, it is also important to follow best practices for installing grounding connections. This includes properly cleaning the conductors before making the connection, applying a corrosion-resistant coating to the connection point, and using a watertight sealant to prevent moisture from entering the connection. Regular inspection of grounding connections is also essential to identify any signs of corrosion early on. If corrosion is detected, the connection should be cleaned and resealed, or the connector should be replaced. The electrical conductivity of a material is a measure of its ability to conduct electric current. Copper has a higher electrical conductivity than aluminum, which means that it offers less resistance to the flow of current. This is why copper is often preferred for grounding conductors, as it can provide a better electrical connection. The resistance of a grounding connection is an important factor in determining the effectiveness of the grounding system. A lower resistance connection ensures that fault currents can quickly and safely flow to ground, minimizing the risk of electrical shock. Galvanic corrosion can increase the resistance of a grounding connection over time, as the corrosion products are often poor conductors of electricity. This increased resistance can compromise the effectiveness of the grounding system and increase the risk of electrical shock. Using copper lugs for all grounding connections helps to ensure a low resistance connection and minimize the risk of galvanic corrosion. If aluminum lugs are used, it is essential to ensure that they are properly installed and maintained to prevent corrosion and maintain a low resistance connection. The choice of grounding conductor material and connectors should be based on a thorough understanding of the NEC requirements, the potential for galvanic corrosion, and the specific conditions of the installation. Consulting with a qualified electrical engineer can help to ensure that the grounding system is designed and installed correctly and that it meets all applicable safety standards. In summary, while dual-rated lugs may be used for connecting aluminum and copper conductors in some applications, it is not prudent to use them in direct contact underground in grounding grids. Insisting on using copper lugs for all grounding connections will help to ensure compliance with the NEC, minimize the risk of galvanic corrosion, and provide a reliable and effective grounding system. Grounding is essential for electrical safety. It provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to operate and clear the fault. This helps to prevent electrical shock and equipment damage. A properly designed and installed grounding system is critical for protecting people and property from the hazards of electricity. The grounding system should be designed to meet the specific requirements of the installation and should be regularly inspected and maintained to ensure that it is functioning properly. The National Electrical Code provides detailed requirements for grounding electrical systems. These requirements are based on years of experience and research and are designed to ensure the safety of electrical installations. Compliance with the NEC is essential for protecting people and property from the hazards of electricity. Grounding electrodes are used to connect the grounding system to the earth. The grounding electrode system should be designed to provide a low impedance path to ground. Common types of grounding electrodes include ground rods, ground plates, and concrete encase electrodes. The selection of the appropriate grounding electrode depends on the soil conditions and the specific requirements of the installation. Grounding conductors are used to connect electrical equipment to the grounding electrode system. Grounding conductors should be sized according to the requirements of the NEC. The size of the grounding conductor depends on the size of the circuit conductors and the type of equipment being grounded. Grounding connections should be made using listed connectors and fittings. Grounding connections should be clean and tight to ensure a low impedance path to ground. Grounding connections should be protected from corrosion to ensure that they remain effective over time. Ground fault circuit interrupters, commonly known as GFCIs, are devices that are designed to protect people from electrical shock. GFCIs monitor the current flowing in a circuit and trip if they detect a ground fault. A ground fault is a condition where current is flowing to ground through an unintended path. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, commonly known as FSIs, are devices that are designed to protect people and property from electrical fires. FSIs monitor the current flowing in a circuit and trip if they detect an arc fault. An arc fault is a condition where current is flowing through an unintended path, creating heat that can ignite flammable materials. FSIs are required in many locations, such as bedrooms and living rooms. Surge protective devices, commonly known as SPD, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges are temporary increases in voltage that can damage or destroy electrical equipment. SPD divert the surge current to ground, protecting the equipment from damage. SPD are recommended for all electrical installations, especially those that are located in areas that are prone to lightning strikes. Electrical safety is a shared responsibility. Everyone should be aware of the hazards of electricity and should take steps to protect themselves and others from electrical shock and fire. Regular inspection and maintenance of electrical systems is essential for ensuring electrical safety. If you are not qualified to perform electrical work, you should hire a qualified electrician. Aluminum lugs can be used in grounding applications, but only if they are specifically listed for that purpose and are installed in accordance with the manufacturer's instructions. It is important to ensure that the aluminum lugs are compatible with the copper grounding conductor and that they are protected from corrosion. Copper lugs are generally preferred for grounding applications because they are more resistant to corrosion and provide a better electrical connection. However, aluminum lugs can be a cost-effective alternative in some situations. The choice of grounding lug material should be based on a thorough understanding of the NEC requirements, the potential for corrosion, and the specific conditions of the installation. Consulting with a qualified electrical engineer can help to ensure that the grounding system is designed and installed correctly and that it meets all applicable safety standards. In addition to the material of the lugs, the size of the grounding conductor is also an important consideration. The grounding conductor must be sized according to the requirements of the NEC. The size of the grounding conductor depends on the size of the circuit conductors and the type of equipment being grounded. The grounding conductor should be large enough to carry the maximum fault current that is likely to occur. A grounding electrode system is a network of interconnected grounding electrodes that are used to provide a low impedance path to ground. The grounding electrode system should be designed to meet the specific requirements of the installation. The grounding electrode system should be tested regularly to ensure that it is functioning properly. The testing should be performed by a qualified electrician. Grounding and bonding are two separate but related concepts. Grounding is the process of connecting electrical equipment to the earth. Bonding is the process of connecting non-current carrying metal parts of electrical equipment together. Bonding is used to create a low impedance path for fault current to flow back to the source. Bonding is required by the NEC in many locations. The purpose of bonding is to reduce the risk of electrical shock. When non-current carrying metal parts are bonded together, they will all be at the same potential. This means that if a fault occurs, there will be no voltage difference between the metal parts, reducing the risk of electrical shock. The NEC provides detailed requirements for bonding electrical systems. These requirements are based on years of experience and research and are designed to ensure the safety of electrical installations. Compliance with the NEC is essential for protecting people and property from the hazards of electricity. In summary, the use of aluminum lugs for grounding applications is a complex issue that requires careful consideration of the NEC requirements, the potential for corrosion, and the specific conditions of the installation. While aluminum lugs can be used in some situations, copper lugs are generally preferred because they are more resistant to corrosion and provide a better electrical connection. It is important to consult with a qualified electrical engineer to ensure that the grounding system is designed and installed correctly and that it meets all applicable safety standards. Remember, the primary goal of a grounding system is to provide a safe path for fault currents, protecting people and equipment from electrical hazards. This requires careful selection of materials, proper installation techniques, and regular maintenance to ensure the system's continued effectiveness. Grounding systems are essential for electrical safety in residential, commercial, and industrial settings. They play a critical role in protecting people from electrical shock and preventing damage to equipment. A well-designed and properly installed grounding system is a fundamental requirement for any electrical installation.